In this contribution, we present a novel hybridization of volumetric and surface-based advection-projection discretizations. We carefully design a hybrid time-stepping algorithm combining a fluid-implicit-particle, short FLIP domain, and an adaptively remeshed boundary element method, short BEM domain, for the discretized incompressible Euler equations. The main idea of our approach is to approximately simulate a large body of water with a BEM, while accurately simulating the fluid inside smaller domains using the FLIP method. As illustrated in this scene, each speedboat is moving within a wireframe box. To simulate the fluid inside these boxes, all we need is the water flow and the sea level at the boundaries. This is provided by the approximate solution of the large body of water using the BEM. On the other hand, the detailed FLIP simulation inside the wireframe corrects the BEM mesh inside, which allows the method to handle complex geometries. In this video, the water surface defines the BEM mesh. It is driven by the turbulent FLIP particles which are accelerated by the speedboat's propellers. The BEM we chose is a surface-only fluids simulator. As shown in this 3D dam break example, it captures 3D fluid dynamics with topology changes. Previous methods have combined a shallow water equation solver and 3D fluid simulations. However, the shallow water waves have different waveforms and propagation speeds. We use the reference FLIP simulation in a shallow tank to drive both the shallow water equation solver and the BEM at the center. The blue and red color in the top row indicate the maximum surface elevation of 0.2 meters, while the red color in the bottom row indicates distances to the closest point on the reference FLIP mesh. The FLIP simulation requires the flow velocity inside the BEM mesh. Our boundary integral velocity interpolation can provide physically accurate flow boundary condition for the FLIP simulation in a Stokes wave scene. The simple nearest neighbor velocity interpolation cannot provide the correct velocity to keep the waveform in the FLIP simulation. We examine the ability of our two-way coupling to extend a small FLIP domain to a larger domain. At the center, the reference FLIP simulation is shown. Our hybrid algorithm at the top left corner matches the reference FLIP simulation. However, without coupling, the pure FLIP simulation in the small tank at the bottom left corner leads to a totally different result. At the top right corner, we show the pure BEM simulation. Please note how the BEM is able to capture very detailed water waves, while the reference FLIP simulation quickly loses the surface waves even at doubled resolution. At the bottom right corner, another surface-only fluid formulation has been employed, which has been adopted from related work. It produces a totally different fluid motion. The irregular shape of the BEM mesh is caused by aggressive adaptive coarsening. In this scene, we show a complex example of a speedboat on the ocean. The FLIP particles generate water splashes, and the BEM mesh can naturally extend the speedboat's wakes to very far behind. As a comparison, real footage is shown here. This top view allows us to see the adaptive coarsening of the BEM mesh and the development of water wakes. Here we show the close-up view of the transition zone. The relevant BEM mesh triangles are removed for clean visualization or turned into wireframes to show the relationship with the underlying FLIP particles. Our method supports overturning waves behind a wedge obstacle. We show the particles together with the mesh colored by velocity, as well as the top layer of the reference FLIP simulation. Initially, the BEM mesh was flat, but the coupling algorithm pulls it towards the FLIP wedge interface. Again, the irregular shape of the BEM mesh is caused by aggressive adaptive coarsening. In this scene, the speedboat follows a serpentine motion, leaving water splashes behind. In this scene, we show the simulation of 3 speedboats riding in a circle computed with our hybrid approach. The rectangular flip domains are highlighted in blue, while the sky is reflected on the water surface corresponding to the BEM domain. The turbulent splashes left behind by a speedboat perturb the BEM mesh. This influence is propagated to another flip domain when it sweeps through. The speedboat's wakes interact with each other, forming a large maelstrom pattern. The surface velocity field, including vertical and horizontal components provided by the BEM, makes it possible to run a secondary whitewater simulation for visual enhancement. We separately render the BEM mesh, the mesh from flip particles with FFT waves, and the secondary whitewater simulation. These results are finally composed. Thank you for your interest in our work and watching this video. The corresponding publication and supplemental material, as well as more information about the authors and our research, can be found on the project website.